in all of the Lewis structures that we've done so far, there's been one central atom surrounded by a lot of outer atoms. Sometimes you can have more than one center. And usually drawing the skeleton structure isn't so easy. We've been just choosing a central atom and then putting everything else around the outside. Sometimes that doesn't work. Let's do an example like that. Let's do the bicarbonate ion. There it is. Now, let's draw the skeleton structure. If I look at these atoms, the carbon is closest to the center of the table, so I'll put it closest to the center of my structure. I'll put the oxygens and the hydrogen around the outside. Now I have, that makes sense, but I have just drawn a skeleton structure that isn't going to work for this molecule. But we're going to be able to tell that there's something wrong here, and we'll know to try a new skeleton structure later. So let's go on with this. Okay, so that's step 1. Step 2, count the valence electrons. Okay, let me see. I got a carbon is 4. I have 3 oxygens, and they're 6 apiece. And I have a hydrogen, which is 1. Would that be all that I would need? 18, 19, and 4 is 23. Is that right? No, it's not right, because there's a minus sign on here. And I have to add an extra electron on there. So I'll have to do 4 plus 3 times 6 plus 1 for the hydrogen plus 1 for the extra minus charge. So it's going to be 24. Now, one thing that would tip me off to that is that if I got an odd number of valence electrons, it would mean that I had a free radical. And those are fairly rare. I will always double check when I get an odd number of electrons to see whether or not I have forgotten a charge here. Sometimes there is no charge, and that's really what you've got, but not in this case. So there are 24 valence electrons here. Step 3, connect the structure. Okay, let's draw our skeleton, and now let's connect it. Now I took away how many electrons? Each stick counts for 2. So that's 2, 4, 6, 8 electrons that I took away, right? So I've got 16 left at this point. Step 4, satisfy the outer atoms. Okay, well that hydrogen is pretty happy the way it is. It only wants 2, and it's got 2. Look at the oxygens. They want an octet. They want 8. They've got 2, so they're going to need 6 more apiece. So, watch what happens here. 1, 2, 3, 4, 5, 6. That one's satisfied. 7, 8, 9, 10, 11, 12. That one's satisfied. 13, 14, 15, 16. 16 is all I've got. I could not satisfy that outside atom. Now, if you fail on step 4, like we just did, we failed because we didn't have enough electrons to satisfy the outer atoms. If you run out of electrons, at this step, at step 4, you better go and try a different skeleton structure and start again. So that tells us, running out of electrons when we're trying to satisfy the outer atoms, that tells us we've got a bad skeleton structure. So there's something wrong with this skeleton structure. Now there is a very easy way for you to fix skeleton structures like this, and that is if you've got a hydrogen attached to the central atom, and we do, why not take it and attach it to one of the oxygens? And you can fix up many of the bad skeleton structures that you'll encounter in Chem 201 that way, that trick. So let's start again. And this time we're going to use this as a skeleton structure. Carbon in the center. And we're going to put the hydrogen, instead of putting it on the carbon, we're going to put it on this oxygen here. So there's our new skeleton structure for step 1. Step 2, count the valence electrons. Well, that'll go just the same way that it did before. 6 and 6 and 6 is 18. 1 more is 19. And 4 more for this is going to be 23. And then 1 more for the -1 charge. That'll be 24 valence electrons that I have. Step 3, connect the structure. I'm going to connect the central ones with the outside ones. Now notice I have 2 central atoms now. I have a central carbon and a central oxygen. How many electrons did I take away? 2, 4, 6, 8. It cost me 2 electrons to draw a stick. So 24 minus 8 is 16. All right. Now I can go on with the next step. Let's see if we run out of electrons now. We try to satisfy the outside atoms. So we've got 16 to play. 1, 2, 3, 4, 5, 6. That one's satisfied now. It's got 8 around it. 7, 8, 9, 10, 11, 12. That one's satisfied. It's got 8 around it. So far I've taken away 12 and I got 4 left. What are the other outside atoms? These are central atoms. That's the last outside atom and it's already satisfied. So I've got 4 left. Okay, so I can go to the next step. Dump the remaining electrons on the central atom. Well, I've got 2 of them to dump on. Let's start with the one that needs it the most. This one only has got 4 and it wants 8. So I'm going to take these 4 and put them here. All right. Now, that's a good trick to do in general. When you have more than one central atom to dump electrons on, dump them on the one that needs it the most. And usually that works out faster. You can make it work out other ways, but it works out best that way. So I should amend this step to dump the remaining electrons on the central atom that needs them the most. Okay. All right, is the central atom satisfied? Well, this one is. It's got 8. This oxygen is. It's got 8 electrons around it. But what about the carbon? It's a central atom and it's not satisfied. It wants 8, but it's only got 6. 2 for each stick. So what can I do? It's not satisfied, so I'm going to share lone pairs with the neighbors. Now, it's got three neighbors with lone pairs, so that there are 3 structures. I could share like that, I could share like that, or I could share like this. Let's draw the 3 structures for each of those possible sharing schemes. If I share up with this one, I'm going to have a double bond going up that way. So what I did was I took this structure and I just took this lone pair and made it a bond there, and that gave me that structure. Now I can also take this lone pair and put it there, and let's see what that gives me. That's going to give me a double bond going up this way. And I'll just copy this one over the way it is. Copy this one over the way it is. Okay? And now finally I can take this lone pair and put it here. And that will also give me an octet on the carbon. That's going to put the double bond going down this way. Remember, we saw that we had to do that to do resonance structures in the last video. And I'm going to just copy this one the way it was. Okay, now, step 6 is assign the formal charges. Let's see if we can cross out any of these structures. If I assign formal charges to this first one, the hydrogen has got one valence electron minus one stick, a formal charge of 0. If you're not seeing how I'm assigning these formal charges, go and watch the video on formal charges again. If I do this one, it's going to be number of valence electrons for the oxygen minus 1, 2, 3, 4, 5, 6 is 0. So that's got a 0 formal charge there. How about this one? Oxygen is 6 valence electrons minus 1, 2, 3, 4, 5, 6 sticks and dots is 0. How about this oxygen? 6 valence electrons for oxygen minus 1, 2, 3, 4, 5, 6, 7 sticks and dots is a minus 1 charge on that. How about the carbon? 4 valence electrons on a carbon from the periodic table minus 4 sticks and dots is a 0. So there are my formal charges for that first structure. And I'll tell you, these look good to me. How do I know that they look good? All the formal charges have to add up to the overall charge on the ion. We said this is bicarbonate ion, and it has an overall charge of minus 1. So all of the formal charges have to add up to minus 1. Everything's 0, but I've got a minus 1 up there. And there's no way I can get rid of that. They all have to add up to minus 1, so something has to be a minus 1 if all the other things are 0. So that's about as good as I can do, so that doesn't look like a bad structure. Now very quickly, try it yourself assigning formal charges to all of these. And you'll see that they're like this one right here, but the formal charges are just moved around a little bit. So these are essentially the same formal charges that we saw with this structure. They're just moved around a little bit. How about this one? Well, this one, try it yourself. This one's going to have a minus 1 formal charge. This one also will have a minus 1 formal charge. So right away I see this one's not as good. This is a 0 formal charge. And what does this have? 6 valence electrons for an oxygen minus 1, 2, 3, 4, 5 sticks and dots. It's a plus 1 formal charge on that. Now that's bad. You're putting a positive charge on a very electronegative atom. Oxygen is a very electron-greedy atom, and you're taking electrons away from it and giving it a plus charge. So that alone is going to make this structure less stable. So if I look at this structure and this structure, I can't tell which one's better. They're both a minus 1 with all zeros, both of these, but this one is clearly inferior. It's got higher formal charges everywhere. So I can reject this structure. And I'm left with those two structures. And there's going to be resonance because I can't tell which one's better. I'll write my final answer down like this for this problem. I'm just copying this one down. Draw your dots really heavy so that they don't look like stray marks. Now I have to put a square bracket around this and a minus sign because the whole thing has got a minus 1 charge. And now it has resonance, so I'm going to draw this double arrow connecting it to the other resonance structure. And this is the other resonance structure that I have. I'm just going to copy it down. that would be my final structure for the bicarbonate atom. Now, notice that there's some resonance. This is going to make the bicarbonate ion especially stable. And what else can we notice? What about this bond right here? Can we say that this bond is a double bond? Well, since it's resonance, this bond is going to be an average of a double bond here and a single bond there. So what I really have between the carbon and the oxygen is a bond and a half. And the same thing with this one. I've got a single bond here and a double bond here, and that'll average out to a bond and a half. So each of these top two oxygens has got a bond and a half going to it.